My name is Gabe Cohn, and I'm going to present Humantenna, a system which uses the body as an antenna for real-time, whole-body interaction. This is work that I did at Microsoft Research, along with Dan Morris, Shwetak Patel, and Desni Tan. And when we talk about whole-body interaction, the thing that comes to mind is the Microsoft Kinect. This is a device which uses computer vision and depth cameras to truly enable interacting with computers using your whole body. The problem is, you need to stand in front of the Kinect device, which is a camera. And if you want to interact elsewhere, you would need to put these cameras everywhere. So I'd like to do a whole body interaction, but I don't want to stand in front of a camera, because I don't want to be limited to doing this only where that camera is, only in my living room. I want to be able to interact everywhere. So I could interact, for example, in my kitchen, in my dining room, or in my bedroom. And I'm going to try to convince you that using the human body as an antenna, we can do just this. With no instrumentation to the environment, that is no camera that we need to stand in front of, and only minimal instrumentation to on the body, we can enable Kinect-like gestures without the Kinect. Now, so this is the vision that I set out last year. If anyone was at my Chi Talk last year, this should sound very familiar. But the question is, how far along are we in actually enabling this vision? So last year, exactly a year ago today, on May 9th, 2011 at Chi, I presented a paper called Your Noise is My Command, in which we explored using the body as the antenna for sensing the location of the user in the home and the position of static wall touches. Now when I say static wall touches, I mean we collected data when the user was touching the wall in one location, and then we collected data when the user was touching the wall in another location, and then we went back and post-processed the data, and we could tell the difference between the two. Now that's a far cry from that whole body, real-time interaction that I presented at the beginning. And one of the problems is that there's no segmentation. In last year's work, we manually segmented when the user was moving. And in this work, we're taking a giant leap forward, in that we're actually demonstrating whole body, free space gestures in real time. So for example, if I wanted to interact with my computer, as I'm doing right now to advance my slides, instead of using a wireless presenter like this, I could use my body. With just a simple device on my arm like this, I could hold it steady, everyone still hear me? And I can simply kick and advance the slides. And since I have everyone's attention now, I'll do it one more time. So I'll kick, and the slides will advance. And I'll come back and show this demo again near the end of this talk. But for now, let me get into how this works. So let's first talk about antennas. I call the project Humantenna. So this is a typical TV antenna. It's called a bunny ears antenna because of the way it looks. And it was designed specifically to receive frequencies at the frequency that TV broadcasts operate. Now this is another kind of antenna. This is a human body antenna. This one is called a teenager, again because of the way it looks. But this one wasn't designed to operate at a fixed frequency. In fact, it's just a dielectric with a complex geometry. So it receives frequencies between about 40 hertz and 400 megahertz. Now this is nothing new. This is actually called the body antenna effect. And it's a source of noise and interference in body area networks and any kind of system that looks at electrical signals on the body. So EMG and EKG, for example. In this work, we're going to take this noise or interference and turn it around and use it as our signal. So how do we do that? So here's our body antenna. And as I said, it receives frequencies between about 40 hertz and 400 megahertz. In this work, we're going to look at frequencies less than about 200 kilohertz. So what's in this band? Mostly electromagnetic noise from the power lines and appliances. So how do we use this noise for gestures? Well, again, we have this noise radiating off the power lines and appliances in the home. And as the user performs a gesture, say they raise their arms up, their arms are getting closer to the lights, for example, which is our signal source. So obviously the signal on the body will increase in amplitude. In addition, because the body has changed its shape, the antenna has changed its properties. So simply by measuring the signal on the body, we can determine the gestures the user is performing. So how do we measure this signal on the body? In last year's work, we had this large backpack apparatus, which had a laptop in it to store data, and so on. This year, we've downsized to a small shoulder bag. And actually, since the Chi paper, we've downsized more to this wristwatch that I'm wearing. So what's in this shoulder bag? Well, there's a voltage probe. We do need contact to the body. It can be anywhere on the body. For this work, we're going to look at the back of the neck, because it's a position that doesn't move when the user's arms and legs move. Then we need to measure the voltage on the back of the neck and digitize it. So we use an analog digital converter, and then send the data wirelessly over a Wi-Fi data link to some computer somewhere else in the environment. So we took this apparatus and we put it on 8 different participants in 8 different homes to see how well our system worked for a variety of users in a variety of different environments. So each of our users went to 2 different locations in the home. One location was a family room, which is typically a large open space, so they're far away from the power lines and appliances, so the signal will be lower. And there's few electronics, except the TV and entertainment system, which is always turned off. The other room was the kitchen, which is typically a very small space with many lights and many appliances, so the signal should be much stronger. In each of these locations, the users performed 12 gestures, which I'll demonstrate for you. So there's both arms up, left arm down, right arm down, both arms out front, rotate, right wave, left wave, bend down, step right, step left, punch, punch, kick, and kick, punch, punch. I'm very good at this, I did it quite a bit. So the users would perform those 12 gestures, and we call that one run, which I'll represent in the lower left-hand corner by this blue box. They then performed 3 more runs. So 4 runs in total at one location, and then they went to the other location and performed another 4 runs. So we call this one session. We then had the users perform 10 sessions in total. So that is 40 examples of each gesture per location per participant. So as you can imagine, this was a very long and tedious study. But I can assure you that none of our participants were harmed in the making of this paper. So we collected all this data, and then we went back and post-processed it later. So we treated our analysis as a machine learning problem, in which there's 3 steps. Segmentation, that is determining when the user is actually performing a gesture. Feature extraction, pulling parts out of the signal to use for classification, that is determining which gesture was performed. So let's first take a look at our signal. So the user performs the rotate gesture, as shown here. And we can see this black curve is the voltage measured over time from the back of the user's neck. Now the first thing we need to do is segment when was the user moving. So we have, from the way our data collection was done, these manual framing timestamps. That is, we know when the user started the gesture, and we know when, sometime after it was completed, because we told them when to start, and then we marked down sometime after it was completed. But we don't know when between those timestamps the gesture was actually performed. So in order to get that, we take a low-pass filter at 10 Hertz, which is this green curve, which I'll call the DC waveform. And what we notice about it is when the user is not moving, it's flat at 0. And when the user moves, it deviates away from 0 volts. So we use this to determine when the user is moving. So now that we have our segmentation timestamps, we can do our feature extraction. So let's first look at a high-pass filter at 40 Hertz. So you can see the AC noise. This is basically the radiation from the power lines and appliances as received on the body. And you notice in this gesture, this AC noise changes over time. It actually increases. Perhaps the user moved closer to a lamp or something during the gesture. And so we want features that will really capture this change. So what we do is we take our segmentation timestamps and we divide the time between the timestamps into 5 equal-sized windows, and then we add 1 window on either side. So we have these 7 feature windows, and we compute features per each window. So first let's look at that blue curve, and we'll take the RMS, or root mean square value, across each feature window. And we get these 7 RMS features. We do a similar thing with the DC waveform, where we take the mean of the DC waveform across each feature window. In addition to these DC and RMS time domain features, we also take frequency domain features. So across each window, we compute Fourier transform, and we take the frequency components below 500 Hertz as features as well. So we take all these features and we throw them into a machine learning classifier. So we use a support vector machine as implemented in Weka, and we train a model per user per location. And then we do a cross-validation in which we fold by session to avoid overfitting. Now what I mean by fold by session is, remember, data was collected in 10 different sessions that were separated in time. So if we train on 9 and test on 1, we ensure that the training and testing sets are always in different sessions and therefore separated in time, so we're not overfitting. Since we have 10 sessions, we do a 10-fold cross-validation. So what are the results? On average, across all users and all locations, we have an average accuracy of about 92.7% for our 12 gesture classification. So random chance is about 8.3%. And this is a pretty exciting result. This means we really can use the body's antenna for classifying gestures. But this is not in real time. This is still post-processing. collected data, we went back and post-processed it. And I said I could do it in real time. So we took this, we tweaked our algorithms slightly, and the details are in the paper, and we created a real-time system. We built a few different demo applications. So one of them, shown here, the user, which is me in this case, performs a gesture, and in real time, we segment when the user's moving. We then extract features, and we classify which of our 12 gestures the user was performing. And so on the screen, it just displays which of the 12 gestures it was performing, and we have a pre-recorded stick figure which gets played back. So it's not actually recording all my joint movements or anything. There's no Kinect in the room. There's nothing on the environment. Simply a sensor on my body. So in addition to this demo app, we also built this Tetris game, which allowed me to play Tetris simply using my body as the controller. So I would step right or step left to move the block right and left. I would rotate with my arms to rotate the block, and I would stomp with my foot to drop the block. And then the third demo application, which I've already demonstrated to you, is changing my slide deck by kicking. So let me actually show you this live again in a little more detail. All right, so this is the live data stream coming off of the sensor on my wrist. And as you can see, again, this is basically what was the green curve before when I talked about segmentation. This is the DC waveform. So when I'm not moving, it's stable. And when I move, the signal moves. So what's interesting is, for example, if I come over here, and again, I hold my arm steady, and I perform a kick, we can classify that as a kick, as shown. I can do other gestures, for example, a wave. I may have been a little too fast. Let me try again. Well, maybe not. But anyway, it was working earlier. So in any case, we can clearly do at least some gestures in real time using the human body as an antenna. So the next question is, what's next? Let me go back to my slides. All right, so what's the future work? So remember initially I talked about the vision of this work is real-time, whole body interaction everywhere we go. Do we have that yet? Almost, but it's not quite robust. So at the end of the day, the signals I'm using for classification are noise signals. So what kind of training procedure is needed so that this works everywhere? How do we deal with the fact that it changes based on location? In this work, we went to one location, we trained a classifier, and we tested in that location. How can we set it up so a user can freely move about between locations and it still works? How do we deal with the signal changing because the appliances in the house are turned on and off? And how do we deal with the fact that users don't perform a gesture consistently all the time? So, for example, I trained this earlier with a wave, and I apparently can't do my same wave again during this talk. It doesn't work. How do we deal with that? And so one way is an improved feature set. We use features which are more robust to these changes in these signals. We could also use a classifier which continually adapts over time to changes in the user and changes in the environment. And right now our system is purely passive. We're just listening to the noise that's coming off the power lines and onto the body. We could also inject a signal, either into the body or into the power lines, that would be much more robust for classification. We'd also like to explore smaller form factor and different point of contact on the body. So as you can see, we've already begun to do this. This is not on my neck, it's on my wrist, and it's clearly smaller than a backpack. But we can continue to do this more. And we'd also like to explore the gesture set and application space of this work. So this isn't my to-do list, this is like the community's to-do list. So what I'm asking you to do is help me go down this list and truly enable that vision that I started with at the beginning. It's really not that complicated. The hardware itself is basically just contact to the body and an analog digital converter. So it can be done on almost any hardware. And the software and algorithms are described in this paper. So I encourage you to help me go down this list and truly enable the system that I mentioned at the beginning. And with that, I'll conclude and open it up for questions. Thanks.
Hey, Gabe, Gregory about from Georgia Tech. You showed the manual segmentation part but you actually had pre-segmented into a small signal, and then you did the automatic segmentation within that. But your demonstration here didn't do that. So how did you make the leap from giving it a small window in which to do the segmentation and going beyond?
So That's an excellent question. And actually, in the paper, there's two different sections. One which is offline segmentation, which is what I described, and one which is the online segmentation, which I demonstrated. And there are slight differences. It's basically just a different filter, and the fact is, in the offline case, we didn't actually need to be offline, it just helped us.
Hi, David Quigley from Georgia Tech. Just a quick question. Have you or do you plan to look at essentially getting a map of how real people do interactions in the space and how that's read by your system? So everyday living and things like that.
We haven't done that yet, but that does sound pretty exciting, and I'd love to look into it, and I also encourage you to look into it.
Edison Thomas with Georgia Tech. I was just wondering what you have on your wrist in terms of what you had that you showed here and what you have there.
So again, the hardware is just contact to the body and an analog digital converter. So essentially, that old big backpack was nothing but an off-the-shelf National Instruments data acquisition unit, which is an ADC. And basically, I have a small one on the board. So that's it.
So you're sending that data to somewhere else for processing, right?
Yes, right. So there's a wireless link on here that sends it.